All right. Let's see. So I'm going to start by sharing the notes again. And um, and then we'll go to the iPad. Oh yeah, another thing I wanted to say too is just that, because it's been a little slower, uh, I'm probably going to push the homework 5 date a little bit. Like, I don't know when it's due right now, but basically figure a few days after that. Um, all right, we can talk more about that on Thursday as well as other logistics. Okay, all right, so this is where we toward the end last time, just that the two parameters in the normal are in fact the mean and the variance. And I remember Tamit mentioned that previously, and then I said, yes, but parameters don't need to be those things. They could be anything. They're just part of the family of density functions. So they define like a two-dimensional, if you will, family of density functions here for every mu, for every possible sigma squared. You get a different thing, but they're all called normal. But it turns out mu is the mean and sigma squared is the variance and sigma is the standard deviation for this. And let's just look at this quickly. Does it make sense mu has to be the mean? Maybe not. Um, One thing I'm thinking is if you think of, say, maybe the first 5 standard deviations on each side, they're totally centered at mu, right? Everything's centered at mu, which is the maximum. And then it's perfectly symmetric. So for every bit I move over to the right, I move over to the left. So using just that intuitive center of mass idea for the expected value, you got to be thinking the EX is mu. So let's just look at this, how you would go about this. I'm not going to do it for the variance, but you're free to follow it in the notes. You should probably, just to convince yourself. So make the classic substitution here, which will simplify everything by letting a new variable z be x minus mu over sigma. And then dz, right, you get the chain rule again, if you will. So you get dx, but you get 1 over sigma dx. This is just a mnemonic. This dz and dx, they have no meaning in and of themselves. There's no such thing as dz and dx, really. It's only in the context of an integral, but but um, but this is true. Certainly, this next step, hopefully, I wrote the integral down correctly. In other words, I have to replace um, 1 over dx, 1 over sigma dx with dz. So I just do that in this next thing. And you see the sigma here, the scale goes bye-bye here, and the dx gets replaced with dz. This really neatly gets reduced to just this single. All this just gets into a single variable z. And what's interesting, though, is out here, the new x becomes this. It becomes mu plus sigma z. All right, well, if I write this as two integrals now, distributing that sum and writing it as two integrals, I get the one on the left is I can take sigma outside and I get z to this. This is an odd function, right? Because it's now the density is centered at the origin here, but I have z, which is going from positive to negative. So this is 0. Where the one on the right, I could take the mu out, and what am I left with is just the PDF of a standard normal. So over the reals, it integrates to 1. So the whole thing is mu. So I think this is helpful to see because, you just prove something useful, and also you can see the method, not to be worried about these things. It's just like in discrete case, only I use the new definition of expected value where I have to integrate uh, over R x f of x dx. So to do the variance, I really need to do e of x squared because then I know it's e of x squared minus e of x all squared. So it's this. So the next thing is just how to integrate e of x squared. The guy next door is using his weed whacker, pissing me off. Okay, anyway, some steps, and then you come to this, but then this minus mu squared gives me sigma squared. So, okay, I want to skip to here now, to this theorem next. So we did several examples last time at the end, pretty basic sort of examples. But now I want to get to this big theorem, maybe the biggest theorem in the class. Yeah, for sure. The biggest theorem in the class, maybe overall, certainly so far. Um, and so first thing you see is the proof is beyond the scope of the class, so there won't be a proof forthcoming. And let's just see what it says, though. All right. So I think we can just look here still, and then I'll go to the. Okay. So say I have a random variable Sn. So I'm just going to label it Sn because I want to take the limit later, and it's binomial with n trials and probability p of a success on each trial. Then I know that the mean of this is NP, right? And I know the standard deviation is the square root of NP1 minus P, or that the variance of it is NP1 minus P. But for one thing, I know that whatever this right-hand side is, what is the mean of this right-hand side? Like if I consider this to be a single random variable now, right? Because Sn is just the random part. And then I subtract off NP and divide by the square root of this. This is just another random, discrete random variable, right? Because no matter what n is, no matter what p is, there's only a countable number of things this could be. Now it's a little different than it's not a binomial anymore because I'm subtracting this off and I'm dividing by this. But basically it's a DRV. The mean is 0 and the variance is 1. Right? Because the expected value of this, if I were to take the expected value of this, you remember the rule about expected value, right? So if I have like, say, expected value of A x plus B, that's equal to A EX plus EB, right? Or plus B. Okay, right? And what is the expected value of Sn? It's NP, right? Because if I want to think of it as the sum of n Bernoullis, each one has expected value P. So the expected value of this is NP. So the expected value of this whole thing has to be, I could take this outside, the bottom part outside, or I could not take it outside the way I wrote it up here. And then I would get the expected value of Sn over this, which would be NP over this minus NP over this. I get 0. Similarly, the variance of Sn, what's the variance of Sn? What's the variance of just Sn? Well, you can show the variances one, two. I think maybe I should go to the iPad for this. So I'm going to hold this off and do it on the iPad in a second. So I just want to get the big things down first. So we take this discrete random variable. We're going to do a few examples. They're binomial, right? Certain probability of success, lots and lots of trials could be like voters, A or B. How many vote for A? How many vote for B? N is a million, right? Something like that. The theorem says in the limit, the distribution is normal, which is freaky on the face of it because you're going from something that's discrete to something that's normal. But okay, say you accept it for now. What does that mean? In the limit, the probability that this thing, this object here, this standardized binomial random variable is less than or equal to any number B is just given by this integral from minus infinity to B of the standard normal. Freaky, right? You're going from something that's discrete to something that's continuous, but it's in the limit. Okay. So, I'm gonna write all this stuff down in a second. So the proof is pretty advanced. It's actually doable for you guys, especially for the basic case, but it would take time. So if you want to do it as a special project with me, we can do it. It would take time. Okay, it's called the de Moivre-Laplace theorem. Abraham de Moivre was early 1700s. He did it for p equals a half. He gave a proof. I've never actually read his proof, but that was true. Very early, which is cool. Like they were just barely getting calculus going, right? And he comes up with this. And then Laplace did it at the end of that century for any p. So he showed for any p, it's true. I think his proof was better. It might have still had a problem, but I think that was pretty much it then. And then the central limit theorem came about, which said if you give me any IID sequence, the sum, or rather the standardized sum, will approach a normal distribution. So you could take anything discrete or continuous, and if you add enough of them up, they start to act normal, or average enough of them up. Same thing. We'll mention this in a little more detail, but we can't prove really any of these in the class. So, but this is always used as the justification for like what they call large sample confidence intervals, where you just assume things are normal, or you assume the sample mean has a normal distribution, things like that. It comes from this. And this was around 1900. By several people, but we can discuss this more another time. Okay, now let me go to the, so the way we're going to use this to show you a little more is that we're going to say if n is big enough, it's approximately normal 0, 1. So this may seem a little weak to you, that you don't have you don't know for sure, but you can, if you do more work, you can find actual bounds and things like this and get probabilistic bounds and confidence intervals for this, how far it deviates from normality in different types of ways. We're not going to do this. We're going to just try to understand it, know how to apply it. The general rule is n should be greater than 10 over the p times 1 minus p, so at least greater than 40. For the p equals 1/2 case, you get 40, but if when p is on the edges, you need more, because it's easier to misrepresent when you have the smaller probabilities of successes or of failures. So you can use this formula. It's not going to really be emphasized in this class, though. We're just going to usually use pretty big numbers and just try to approximate with it. All right, so you see I have some examples picked out for you here, and it's similar to the stuff in the homework. And I just want to do a couple now and uh and uh and then um and then wrap it up by in about 35 minutes. This is the plan for today. I do think it's important to check in today. That's why I did this. Um, thanks for coming. I will post it online as well. All right. So let me, before I go there, I just do want to make sure this was clear because I realized that that didn't come off very well. And so let me stop sharing here and share over here. All right. Yeah. So I just wanted to make sure this part was clear. Um, yeah. So we take Sn, right? Say that's binomial. NP. Okay. And then what they call standardize. Subtract its expected value and divide by the standard deviation, square root of the variance. Um, Here, I'm not going to rederive these things, but we're going to say this is, we could say standardized Sn. It's discrete. We could say the mean is equal to 0 and the variance is equal to 1. So it makes sense that it should approach. So then as n goes to infinity, the limit n to infinity of the probability that Sn minus Np over this say less than some number b is equal to minus infinity to b 1 over root 2 pi e to the minus z squared over 2 dz, which is just p norm of b. Well, I just want to point out something. It makes sense that it has to approach the standard normal, right? Because it's standardized. The mean is 0 and the variance is 1. So it definitely wouldn't make sense if this was any other kind of normal. The fact that it is normal, though, is really, truly one of the wonders of mathematics. I mean, it is not to be underestimated how insanely miraculous it is. And if you do the proof, you see all the details. But to me, it doesn't destroy the miraculousness. It still seems miraculous even after you see the details. It's not like, oh, well, that makes sense. It's just still like, yeah, but I can't believe it. Or who thought of that? Okay, who thought to do that, to check it? All right, now enough yapping. Let me come back here. Okay, so do you see that the variance of this is 1? So let me just make this a little more clear. So to get the mean, we have E Sn minus this whole thing over this. Okay, but this is just equal to, I could take this outside, right? I know I just said this, right? But then what is the mean of a binomial? NP, right? So it equals 0. All right, now what about the variance? What's the variance of Sn? Well, if I think of Sn as the sum of n Bernoullis, IID Bernoullis, this is the variance of x1 plus dot dot plus xn, where x1 dot 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 xn, IID Bernoulli P. And we said previously that if we have the expected value of the sum is always the sum of expected values. So we didn't need to assert the independence, underlying independence of Sn. But for variances, it also is the variance of the sum if the terms in the sum are independent. Since these are independent, I can do that. I can say var Sn is equal to the sum of these, but they're all the same. They're also IID, so I can just say it's n var of x, any of them, right? x1 or xi. And the variance of the Bernoulli, we did see, I think you are pretty good in this, is 1 minus p times 1 minus p. Okay? Okay, now let's take the variance of this. So if I have the variance of this thing over here, let's write it like this, square root np 1 minus p minus np square root np 1 minus p. And I'm going to start talking to you now. Now, what do we know from before? From that day we wrote all the properties about expected value and variance. If I have the variance of ax plus b, what is this equal to in terms of the variance of x?
That's a squared times the variance of x.
That's right. Yep. And we showed this from the definition. This is a squared times the variance of x. The intuition is there's no variance in b, and that variance is a squared measure. So when I multiply, I get a squared. So that's a good way to remember this. Right. So I just do the same thing here. This is b, right? And this goes away. So this is just equal to 1 over n p 1 minus p. This is a, okay, this is a, and I just square this times the variance of Sn. But that's np 1 minus p, and I'm squaring this, so the whole thing is 1. All right, it works in other words. We get something with mean 0 and variance 1, but just like the fact that, if I take a linear function of a normal, I get another normal. The fact that this converges to a normal distribution is beyond the scope. By the way, if you're interested in this, you can come see me. I'm very interested in it because there's so many cool things in this, in the proof for it. And especially this case, the binomial case, when the central limit theorem uses more advanced mathematics from measure theory and things like this. And in a way, it's not as insightful. It has other insights. But this has some really good insights too, if you just look at the proof that doesn't require that stuff. Okay, so I think I just want to go on and do some examples now for how we would use it. So I'll just make this note here. Although the result is for the limit only, we will often be requested both in the class and in further work to approximate Sn by a normal random variable. Okay, so that's the point of the next step to show you this. You should always see the words like use a normal approximation, so then you know what they mean. And we're going to do, I did some numbers here and you'll see how close the numbers are. And maybe we'll do some stuff on R2 to see this today. If not, we'll do it in the lectures to come soon. Okay, about 25 minutes to go. I just want to make sure I'm not holding you over past what I said. So example one, let's just say we start with something simple. And I want you to think about this following application. Like it's election season, right? It really is election season now. And so think of this to make it interesting for yourself. Think of it as it doesn't have to be Trump and Harris, but just think of it as two candidates that are running, and X is the count for one of the candidates. Okay, so we have X is binomial. And we can also think, oh, well, what about other third-party candidates, other candidates? Throw them in the garbage. Okay, just for now. I mean, they may be better candidates, but we're not going to consider them because we just want to look marginally at the probabilities. In other words, we want to discard any votes that aren't for the two candidates because really we're going to say that's what we're focused on. And it is a righteous way, if you think about it, to do your analysis, because in the real world, that's what happens, right? You have a bunch of stuff that's like, I don't know, I don't care, some other third party thing. Well, those don't factor in. So you're just going to those two. So it makes sense. So you just think about it as a coin flip. And we're going to, for now, just start with the question, supposing, or say our hypothesis is that candidate A has a probability of being picked. P, that's our hypothesis, of 0.6. So 3 out of 5, we're hypothesizing are for candidate A. Okay, Elizabeth Warren, John Deaton, I don't, you can go down the list, okay? Or questions, ballot questions. Question 2 is a good one if you're in math. Anyway, okay, so say we want, now, here's the thing I want to know. Say I'm doing this finite sample of only 100 out of a big population, say 2 million or something, whatever it would be, 1.5 million or whatever it's going to be. How useful is this? I mean, clearly I could have all 100 possibly pick the candidate B who has a 0.4 probability. That's possible. I could then go marching on and say, well, it's a landslide for, so so let's get some sense of how likely this is. So what I want to know is if I have a 60% chance of getting a success on one vote, what's the probability if I take 100 votes that less than or equal, I'm not the majority, I'm not 51. Okay, so we want the probability, this is right from the notes, we want the probability X is less than 50. Okay, well, we know already this we could do in R, and I probably would do it exactly if it was this. But a lot of times you want to do the normal approximation anyway. So it's K equals 0 to 50, 100 choose K, right, et cetera. 0.6 to the K, 0.4 to the, to the 100 minus K, right? And we can call the R command in one word. It will take it microseconds to do it. P binom 50, 100.6. And this just means this. This is exactly what this means. It combined, this 50 is this 50, this 100 is this 100, this 0.6 is this 0.6. It's, in other words, it's the CDF evaluated at 50. Okay, and if I do this, I get to first 3 significant digits here. It's something like 0.271. I think. So pretty unlikely, right? So even at 100, you got a pretty good shot. You know, and 60 is pretty close to the middle, but it's pretty unlikely that that would happen. So for you people who know statistics, you would say, you know, if you were trying to work with a 5% significance level, you would say there is significant statistics here to show that probably that maybe 0.6 is wrong, that it's less than 0.6. Okay, let's use our estimate now, our normal estimate. So I'm going to start, remember, X is defined here. I'm not going to lie. I'm not going to just cheat and write crazy things down. We're going to keep it as much math as we can. So the probability X is less than 50 is equal to the probability X is less than, I could write or equal, but I'm gonna drop that, 50.5, right? Because this is discrete. So X can only be 50 or 51. So this is a true statement. The reason you do this is called correction. Does anybody know? For continuity, which is coming up. I do it here just because it's true still. So far, it's true. Like I could have typed 50.5 here. I'd get the same number. Okay, now I want to standardize it though. Keep it well defined. That's the main reason you standardize these. Actually, for finite n, it doesn't really matter, but the reason you have to really write it like this is because as n goes to infinity, this would sort of stop making very much sense in a good way. With this would go to infinity, this would go to infinity. I mean, it just gets at best confusing. So we want to standardize it and keep it in check, you know. Okay. So next step is to standardize this. So I'm going to write like my Sn thing. I can still call it X though. I'm just going to have probability. Notice I could have called that S60 or something, but we just call it X. We usually do. So I'm just going to take X, standardize it, subtract its mean, and divide by its standard deviation, which is 24. Do you see that? 0.6 times 0.4 times 100. So the square root of 24. And I want to say that's less than or equal to 50.5 minus 60. So minus 0.95. Sorry, minus 9.5. Over square root of 24. Okay, so far, no black magic or anything. Everything's fine. But here I go to the black magic. This is called, you want to seem like you really know what you're doing, or you want to make sure you get your credit and stuff. You can write CLT here. I write this because it's smaller. It's the de Moivre-Laplace theorem. You could write that. You could just write theorem. You could write approx, anything. Let me know if you want. Here, if you don't, it's okay too. Okay, so it's approximately that integral. So remember, less than or equal to this here. I'm going to put this in here, and this is actually now, if I put the number in here, minus 1.9, right? Because this will be about 5. So you can see it's about 2, minus 1.939. And this gives me 0.0264. Okay, right. So the central limit theorem is the general case. The Moivre-Laplace theorem is a special case of it. It falls into that class. So if you want to sound cool, you could say central limit theorem. That's true. It's the same thing. It's just more general, has other cases too. All right, so look, let's see, what was I going to do here? So where was our other number? Oh yeah, here. Pretty good, right? Pretty good with only 100. And in the notes, it says that if I take the relative error, which is usually defined like this. You put your estimate in here. So you put your estimate, you subtract the true, divide by the estimate, and you get some number. When I do this, I get 0.00086 divided by 0.026. Yeah, something like that, right? Is about 3.3%. Right? Let's see, take 3 decimals over here. Yeah, 0.8 over 26. 8 over 260. Yeah, 3.3%. Okay, that's not bad. It's not great, but it's not too bad, right? Looks pretty good. You don't want to see something like 30. Okay, so let's now try it with a bigger number. I have x is binomial. So what this tells you is actually anything. It gives you some significance, right? Some level of statistical significance already. Pretty unlikely that that would happen. So if you had set up some hypothesis test where that was your rejection region or something, or you wanted to make a claim, you could say, look, I was less than this. I have, this is the value here. And 0.02 is pretty small, so it does suggest something might be going on. Okay, next one. Say x is binomial, and now I raise it up to 1,000, and I'll do this too, just because I did it in the notes. So I'm doing 2 things that should improve it. I'm putting p more toward the middle, and I'm taking another order of magnitude of samples. And I'm going to say, what's the probability? And I'm also going to look at even further away from the mean. So probability x is less than or equal to, say, 450. And I don't know, actually doing this again now, I don't know what it is, what the number came out to be. I'm going to glance at the notes, of course, and make sure. But we're just going to repeat the steps. So far I haven't made an approximation, and I'm going to say the probability x is less than 450.5. Does anybody, I'm going to stop for a second. Does anybody want to weigh in on what this 0.5 is all about? I couldn't hear you, Sylvia, if that was you. Yeah, so that's like, look, the binomial can only be 450 or 451. It can't be 450.5. But the feeling is that if you want less than or equal to 450, you want to include 450. So you should meet 451 halfway, basically. And this will give you a slightly better number, slightly more accurate number. So that's the plan. So you want to think about the inclusivity or exclusivity of the operator here, as well as, yeah, and then to determine, if you want to make a correction here. Okay, so this is what we do here. I want to include this, so I don't want to just shave the edge off here. I want to go up to 450.5. This is the way the binomials are really used. And 1,000 is a pretty actually reasonable sample for politics. You might go higher. For sure, you might go higher if you have a professional group and everything, but you're already starting to get somewhere here. So this is equal to probability. Of course, there are other issues. I'm not trying to pretend this is the only statistical issue. I am being a little bit idealistic here, try to get you excited about it. But okay. So I'm going to standardize it, subtract off its mean, divide by its standard deviation. I'll do the same thing on this side. You have to do the same thing on both sides. The inequality is maintained. I'm only dividing by a positive number, so I can say minus 49.5 on the top here and divide by the standard deviation. Does everybody see that comes from P, 1/4, 1 minus P, sorry, P 1/2, 1 minus P 1/2 times 1,000. So I get 1/4 times 1,000 or 250. Okay, and this is the number, if I just to clean it up right in line here, minus 3.13. And I already know that's 3 standard deviations to the left. So it's going to be pretty small. And if I do this, I get, now I can just use P norm. But now I'm going to the approximation. So P norm minus 3.13, which is approximately, or you could say equals at this point, 0.000872. So highly unlikely. Even if, now remember, we're closer to the mean here too. We're at 1/2. We're assuming they're equal. Okay, we're assuming they're equal, and they're saying, what's the probability candidate A is less than or equal to 450? Okay, and that candidate B then would be greater than or equal to 550 or greater than 550. Well, that's really unlikely to happen if the probability is 1/2. Okay, and this tells you how likely it is. It's less than 1 in 1,000. Okay, 8 in 10,000, 9 in 10,000. Okay, so you can do the actual if we wanted to check the true, if we did P binom, just to compare it. I just put 450. This is just the CDF function. 1,000, 1/2. And this is super close. This is 0.00065. Super close. The relative error here, I won't bore you with. Even though I like computing relative error, I won't bore you with it. So this is about, now don't get confused by this 8, but it's 0.80%. Okay, so remember, this refers to the difference between this one, and then divided by this one. It's a little different. It's not as extreme. This looks really good as an estimate. You could just see it's really close, very small, and it's close. You're away from the center. The relative error brings you back to reality a little. It's about 1%, a little better, but that's still very good, actually. So, okay. All right, let's see. I wanted to stop in about 8 minutes. So let me just see here. I do think we just want to do one more example here. And yes, and I know which one to do. Okay, so you can read these in the notes too. These are really right from that. Okay, so say for the fourth one, we're going to say, or the third example, say we have Sn binom. I'm going to leave n as a variable now, and 0.7. Okay, and I want to see, you see, because you could see how when n got bigger, it got less and less likely that something weird would happen. So I can now make up a question like, how big should n be? So the probability Sn is greater than something is at least something, right? Because I know at a certain point, it's going to be unlikely for Sn to be too small in terms of n. It's going to approach 0.7n, right? So if I say, how big should n be? I actually have the problem here. So using the normal approximation, so let me write it down. Use CLT approx. Find minimum n. So probability Sn greater than n over 2, because I know this has to get big. because it should approach 0.7 n. So of course it's going to get bigger than 0.5 then. Is greater than, say, greater than or equal to 0.99. By the way, you could use Chebyshev, but this is more powerful. Okay, so it's sometimes interesting to compare them. So here's our solution. It's really just the same thing. You would all have figured it out with enough time. So I say the probability Sn is greater than n over 2. Now, there's a slight difference between whether n is even or odd. So let me put this in. So this is going to be equal to the probability. Let's see, if n is odd, it's cool, right? Because then I get something that's not ambiguous, right? Not on the line, and I don't have to correct. So this is the probability. Oh my God. I want to put them both in here, but here, let's do it like this. This is the probability Sn greater than n over 2. I could just leave it like this if n is odd. But I should probably do something else if n is even, right? So it's the probability Sn is greater than, so if it's even, it will bring me right back to that point. And since I want to be strictly greater, I should add a half. So greater than n over 2 plus a half. I don't want to be right on the line. Technically, that would be wrong. And statistically, not as good practice. So n even. But the thing is, I'm just going to wave my hand anyway. So when n is big, the 1/2 is not significant. So we just throw it away. So discard it, because otherwise the problem's harder and pointless too. It's dumb to do that. Okay, we got 4 minutes to go. We got plenty of time. Okay, so I discard that. And so I'm just going to stick with this. Okay, so we have probability Sn greater than n over 2 is just equal to, I standardize it, Sn minus 0.7n over square root 0.21n, right? I think 0.7 times 0.3 times n is greater than the right side minus 0.2n, right? 0.5 minus 0.7 over square root 0.21n. And here you see why you needed to discard that, or why you wanted to anyway. You want your n's to cancel here. You don't, it's confusing otherwise. So in fact, I can do some cancellation now. I get that this is equal to, just do the division here. I get minus 0.436. I'll divide n by the square root of n to get the square root of n. Okay. Now, what do you see? That's good. Now, by the way, we're going to use the fact that this is approximately normal 0, 1. Okay. So, and I have a negative number here, right? So no matter what n is, this is negative. So as n gets bigger, this value here, this minus 0.436 square root of n, starts sliding to the left as n gets bigger. And so, of course, a standard normal is going to be greater than this to any degree. It's going to go to 1 in the limit. So we know there's going to be such an n where this is true, okay? So take a pause here when you're here. we have this is equal to, or now we go, this is approximately equal to the probability that Z, you really want to make it clear, normal 0, 1 is greater than minus 0.36 square root of n. And now you can see if n is big enough, this can be any number up to 1, basically. So if we set this equal to 0.99, we are just left with one challenge, which is to find how to now get that answer, right? So if you look at the standard normal, I'm right, I got a minute left, but this will just take 2 minutes or so. So at some point over here, there is this value where this is 0.01 over here, and it's 0.99 for the rest of it. So I need to know what this value is. So it's the inverse CDF. The inverse CDF of Z, and that's called Q norm. So Q norm in R. Okay, so it's that point to which on the left, there's 0.01. So it actually would be 0.01. Okay, so I need to do yeah. So let me just make sure. Just hold on. I put this arbitrary pressure on myself. Yes. So what is that? This is going to be yeah. So this is going to be, this turns out. So if I put this in here, I have sorry. So if I have Q norm of 0.01, and I get minus 2.3263. So the probability that a standard normal is less than 0.01 happens, is less than minus, sorry, I'm getting befuddled now because is less than this is 0.01. So this is what I want to make it, because then I know it's 0.99, that it's to the right of this. So we just set those two things equal. I get minus 0.436 square root of n should be equal to minus 2.3263. And after rounding this, so I divide by 0.4, I get something bigger than, like 6 or 7, and then I square it. So I get n equals, maybe it's 5, actually 5 or something. So I get n equals 29 after I wear it. So it's the minimum integer, n equals 29. So did this make sense? So with only 29 samples, I have a 99% chance that out of 29, say, flips of the coin, when the probability of heads is 0.7, I have a 99% chance that that more than half are heads. So if it was 29, that 15 were heads, 15 or more, will be a 99% chance. You can think about elections. You can think about other things. There's some different homework problems like overbooking a flight and things like this. It's all basically the same idea. Define it, model it in terms of a binomial so that you're solid on what you're actually doing. Then just employ the central limit theorem or the mod Laplace theorem, if you want to call it that. Okay, that's all I got. I'm going to stop the lecture. We'll continue next time. The next thing, notice the notes, skip a few pages. And we come down here and we're going to start the gamma function and the exponential function. We'll talk a little bit about logistics and a little about using the computer too. But that's all I got for now. So does anybody want to go on the record or anything before I stop recording? All right. I'm going to stop recording. If you want to linger and talk, that's fine. Where the hell's, oh, stop.